Okay, so hello everyone. So welcome to our this week Rogers Efficient AI seminar. And today we're very glad to have the Professor Mingu Kang from the UC San Diego to give us this talk. Professor Kang is currently assistant professor of the electrical and computer engineering at the UC San Diego. He received the PhD degree in ECE from the University of Illinois. And from 2017 to 2020, he was a research staff member of the IBM TJ Wilson Research Center, and where he designs the machine learning accelerator architecture and has been successfully commercialized in the IBM server. And from 2009 to 2012, he was with memory divisions, Samsung Electronics, and he was involved in the circuit and architecture design of the phase change memory. He's a recipient of the Intel 2022 Rising Star Award, UIUC CSL Best Thesis Award, Michael Topic Honorable Mention, and IEEE ISCA's Neural System Application Best Paper Awards, and many other scholarship and awards. Okay, so let's welcome Professor Kang to give us this talk, Ultra Low Power Machine Learning via Hardware and Software Co-Design.
Okay, yeah, thank you so much for the kindly introducing me. So I'm so glad to meet you, everyone, and also interact with you through this opportunity of Rutgers Efficient AI Seminar Series. And also, it is my great pleasure to present the piece of my work about low power machine learning, hardware and software co-design solution. So Professor already introduced me. So again, my name is Mingu Kang from UC San Diego. It's been less than 3 years since I joined UC San Diego. So I'm quite relatively young faculty in UC San Diego. And then I designed, before my joining UC San Diego in IBM Machine Learning Accelerator Architecture team, I designed this is the single core version at the very beginning, and then multi-core and more scalable version, like up to 64 core extendable version. And this was actually training and also inference, dual purpose processors, and also had very the reconfigurable to cover wide variety of machine learning models through this one single chip. And then it was actually commercialized by being embedded as a key feature of the IBM Z mainframe system. And earlier, before that, in Samsung Semiconductor, I was a microarchitecture and circuit designer in phase change memory team. Yeah, currently in UC San Diego, I'm focusing end-to-end VLSI implementation for machine learning and also signal processing algorithms. And I'm trying to apply not only the conventional digital AI accelerator like that I did in IBM, but also I'm focusing a lot of the emerging computing topologies like in-memory computing, in-sensor computing, neuromorphic computing, or switch capacitor-based analog computing, hyperdimensional computing, and many others. So both conventional digital route and also emerging compute route. And specifically, I'm focusing the vertically integrated research across circuit stack, architecture, device, and system algorithm with both CMOS and emerging devices. That is why our group's name is VVIP Lab, Vertically Integrated VLSI Information Processing Lab. And our group is also trying to validate our scientific finding through the silicon fabrications. So that by measuring the chip, we are trying to validate the concept that we are proposing. Right. Okay, so today's talk, given the limited time, I am going to focus on the 3 projects, and we will showcase how our group have been performing the vertical connection of the research. The first one is the system and architecture combination. Second one is architecture and also new device. And third one is circuit and architecture's combination. So these 3 topics. So let me begin with the introduction and motivations. So, as you might know already, the ChatGPT is actually very useful. So this is an example. I said, please build itinerary to San Diego with kids. And then, as you can see, day one, they suggested San Diego Zoo. And then afternoon, they suggested Balboa Park, which is pretty close from the zoo. And also evening, they also suggested La Jolla Cove. So indeed, as a San Diego resident perspective, this is actually pretty reasonable, the plan. And not only this kind of ChatGPT, in many different ways, like a navigation system, translation, language translation, autonomous driving, sentence auto-completion, in many different applications now, AI is being penetrated into our daily life deeply. On the other hand, maybe did you know that carbon emission problem, like one big transformer's train takes 10% equivalent carbon emission that generates equivalent carbon emission of 10% of one passenger's flight from New York to San Francisco. And also given the recent research, one big transformer's the neural architecture search generates the carbon emission 5 times more than the one car's lifetime. So we need to feel that as a researcher, we need to be more responsible for this kind of carbon emission. And then this is actually showing the importance of low power. Carbon emission is equivalent to the low power. If you reduce the power consumption, then it is reducing carbon emission. So this is tells us again the importance of the low power AI accelerator. So this is not the optional problem, but this is now really the matter of survival. Okay, so then how am I'm trying to address this kind of problem, low power problem. So first project is data aware low power transformer accelerator. The first research was published last year, ISCA. And then transformer is now really changing the paradigm of AI. So if we take a look at the transformer architecture as an example, that is not really special. Like a lot of the residual network layer, feed forward, meaning the fully connected layer, nothing special. But the only key feature is the multi-head attention. And so multi-head attention is it accounts for more than 50% of the total runtime and a lot of power. And more importantly, when the sequence length is longer, that means that when the sentence is longer and longer with many words, then this portion is exponentially increasing. So this is one big problem. So our group is trying to address this problem by proposing some low power attention acceleration. So I guess actually many of the audience already know what is the attention. The attention is the key computing kernel. By the way, the attention was here, right? And then multi-head attention, meaning there are multiple attentions are processed in parallel. But if we take a look at just simply the one attention layer, the attention is, the key feature is basically checking the correlation between two tokens, token meaning words. So by checking the correlation between two words, for example, Morris and Ellie, for example, by comparing the relation, we are trying to get the context of the sentence. So if I explain, so actually this is, if you do not know the attention mechanism, it might be a great opportunity to study. It is pretty simple. I will give a one-page summary. So all of the words, which means the tokens, are supposed to generate Q, query, key, value, 3 vectors. Based on there is a WQ, WK, some generation matrix, and by using the fully connected layer through for the input, anyway, we generate QKV vectors. And then now we check the correlation. Let's say that Ellie and Morris correlation is checked by Q3 dot product K1, then 0.1. Q3 multiply K2, 0.3. Q3 multiply K6, 0.1. So this is actually the score, correlation score. And then we simply go through the softmax to normalize. And then the normalized value, the value will be multiplied with the value matrix. V1, 0.01, V2, 0.41, V3, 0.45, and so on. So, and then finally, these contents will be summed up to generate final decision result of the Z3. However, this is an example of computing the token alley. We need to exhaustively compute from the model to the sister, all of the words. We need to iterate this process. So as you can see, the computing complexity is proportional to large O and to the power of 2. So that is why when the sequence length is getting longer and longer, this portion is exponentially increasing. Okay, but we have some opportunities. So this visualization shows the correlation score between two tokens in terms of the strength of the line. So maybe you might notice in one shot, indeed, most of the connections are very weak. So even it is not visible, right? Which means that the correlation is very weak. And then connection is very weak, meaning near zero. So this is actually great opportunity because those kind of near zero values we can skip. It doesn't impact on your final result. It is inconsequential. So now let us go back to our original table. So indeed, as I mentioned, that once we calculate the correlation, many of those are actually near zero. So let's assume that we don't know what is the threshold, but anyway, for a certain threshold, let's say 0.25. And if those score is smaller than 0.25, we can simply drop those values to be zero. And then we can just ignore and we can skip those computations. So this is indeed actually great opportunity because we can skip all of those tokens computation efficiently. But this gives the opportunity and then challenge at the same time. Because indeed it gives the opportunity to skip many computation. However, one problem is how to find the threshold. I mentioned in this figure, I gave the threshold of the 0.25. But how do we know that optimal threshold? If the threshold is actually very high, we can skip more tokens. But if we skip too many tokens, then computation accuracy might be degraded. On the other hand, the threshold is too low, then we cannot skip a lot of the tokens. So how do we balance? Especially we have many layers. If you take a look at the GPT-3, it might be 96 layers, if I remember correctly. And then each individual layer, as I mentioned, multi-head, meaning that there are multiple attention layers. So all of the layers and all of the thresholds, how can we find? So this is actually one big problem. So ideally, we want to go for the direction of the last one. We want to push the threshold as high as possible so that we can skip a lot of tokens that's shown here. But we want to maintain the accuracy at the same time. So this is our goal. So the research direction is, let's say that threshold, let us include the thresholding layer itself as a part of the network model. So we included the threshold as a part. And then now we are trying to train this threshold as a trainable parameter. So this threshold will be learned along with other trainable parameters together. So during that process, maybe the weight, the trainable weight, and this threshold will be co-optimized, and then those will be balanced between the sparsity and accuracy. So this is our general idea. The threshold will be auto-tuned and automatically learned, and then those will be optimized. Another problem is, let's say that, okay, based on the threshold, we can skip a lot of tokens, but if we skip at the end, we can merely skip this last stage, which is not really efficient. So our goal is, let's say if there is a redundant tokens, we are supposed to skip as early as possible so that we can skip all of the subsequent computing pipelines. Yeah, so we indeed tried to apply by including the thresholding layer. And then threshold, we hope that those will be learned. So threshold function is actually a little bit bizarre as shown here. If the input is larger than threshold, we just pass the value as shown here. On the other hand, if the input is smaller than threshold, we need to give large negative value. So why negative? Because right after that, there is a softmax. Softmax computation is basically e to the power of x. So to make this guy to be 0, we need to give very large negative number as shown here. The problem is, do you think that this shape is differentiable? No, this is non-differentiable because of the discontinuity around the threshold here. So this kind of discontinuity, because it is non-differentiable, it prevents the gradient flow. So gradient does not flow, it means that training is not possible. So to address this issue, we proposed soft threshold. So based on mathematical approximation, as shown here, as a reference of the threshold from the right side and left side, we used a little bit different functions, tan h function. And then indeed, if we increase the parameter of s, meaning the slope, if we increase a lot, this shape is actually sharper and sharper. The slope is very sharp. Then now the right function is actually very reasonable approximation of the left function. So in this way, so we can let the gradient flow because tan h is differentiable. On top of that, also so anyway, so this is actually good approximation and also still allows the gradient flow so that the training is supported. Now we barely let the gradient flow. So training barely work. But do you think that that is enough? No, because we need to tell the trainer, hey, please train to maximize accuracy and also sparsity. So we need to give some guideline for the trainer. So those guideline is basically these two terms, accuracy term and also regularization loss. So basically regularization loss is, please count how many of those, so here earlier I said K and the next page is C. So it might be a little confusing, but yeah, those are the same thing. So sorry about that. But if the score is unpruned, bigger than pruned result, then we are giving 1 point penalty for the loss function. So we basically count how many tokens are unpruned, how many tokens we failed to prune out. So based on that, now we are adding those the score, the loss, the penalty on the loss term. Then the trainer will try to minimize the loss. So this part will be minimized, and this part will be also minimized together. So because of that, trainer is trying to reduce the unpruned token, meaning that maximize the pruning ratio. Okay, and also this is another problem is basically we are implementing this kind of the counter. How many of them are unpruned? So this counting function is not differentiable, first of all. So because of that, we also, with a similar approximation, now we use the sigmoid function. So by using this sigmoid function, now we can also make a rough, the approximation of the counting function. If the value is bigger than something, then it is unpruned. So then please count, please give the 1 point deduction. Otherwise, if it is pruned, then 0 point deduction. So based on the sigmoid function, we can sort of emulate those the behavior, but still that is differentiable. So based on these kind of the mathematic tricks, now the training works magically. As shown here, as training epoch goes on, the threshold is increased as shown here. At the same time, because of that, many tokens are pruned out. So their sparsity is increased as shown here. On the other hand, the training loss, which is the combination of the accuracy loss and also sparsity loss, those are also co-optimized as shown in this graph. So we can say that we successfully finished our job. Okay, now the pruning rate, pruning ratio wise, we tested a lot of different types like vision transformer, language transformer, and also GPT and many others. And then on average, we achieved around 75% of the pruning ratio, meaning that we can skip many of them, but only we need to compute 25% of the important tokens. So that is the message. And then your natural concern is whether the accuracy might be fine, but indeed, because we co-optimize the accuracy loss and sparsity loss at the same time, as shown here, though, you won't be able to see any visible difference in terms of the accuracy between two bars, meaning that accuracy drop on average was just 0.3%. So we cannot say that there was any impact. So we cannot see any virtual impact in terms of the accuracy. Now you might recall that I told you that we are trying to skip the computation as early as possible on pruned tokens. So the redundant tokens we are trying to skip as early as possible. So we also implemented that based on bit sequential processing and early stopping. The basic idea is we compute the MSB first, and then please check whether this is bigger than threshold and smaller than threshold. Even we have the remaining bit precisions, right, LSB side, but even considering those possibilities, this token is ever possible to be bigger than threshold. If not, we just early stop and prune. And there is a chance that this is actually bigger than threshold based on the following the LSB bits. Then we compute one more bit, and then we compare. And also one more bit, we compare, and so on. So in this manner, we can reduce the computation and also memory access. And also, even before we fully compute the query multiply key dot product, we can sort of make an early decision. And then, as you can see, out of the entire bit precision, only half of them gives actually already matured pruning ratio. And then this is the structure of the hardware architecture. So this is the query multiply K processor. There are multiple cores. And also, whenever there is an unpruned tokens, it goes to the FIFO. And then those FIFO gives the softmax. And then finally, multiply V, meaning the value vector multiplication stage. So this is the synthesized and also PNR to generate the post layout results. And then as you can see, there are many QK processor, like a 6 QK processor, and there is a memory as well here. And then there is also the softmax value processor and value memory. And there are many QK processors. Why? Because as I commented, many of the tokens, meaning that on average, 75% of the tokens will be early stopped and pruned out. So many of them would not reach to the multiply V stage or softmax stage. So because of that, we have many QKs, and only one of them, statistically, some of them survive unpruned, then that token goes to softmax and also value processor. And because of that, the QK logic consumes the biggest area as shown here. And this is the 65 nanometer result, and we achieved 800 megahertz clock frequency. Now, given all of those type of optimizations, we achieved the energy benefits and also delay benefit. So to summarize, we could achieve 4 times energy savings and also more than 2 times speed up on average, and also 75% pruning rate on average, and also with quite negligible accuracy degradation. So this method was done by trainable threshold, and threshold and the other parameters are co-optimized as a trainable parameter to boost both accuracy and sparsity. So this is the summary of the very first product. Okay, so and then the next project is now the accelerating transformer with in-memory computing, which has been published in Micro 2022. So earlier I showed some similar figure. I want to make us stop the prune as early as possible in the middle of the QK. But now I want to push this pruning even before QK computation, even before you move the contents from the DRAM main memory to your processor. Even before that, we want to make an early decision with in-memory computing. So this problem is also for the transformer. And then now we started to focus on different problems. So axis shows that on-chip cache memory size. Then how large your cache memory? Let's say that to process one layer, our cache does not have entire space, but our cache size can store only 40% of the contents for the layer processing. Then in that case, as you can see, DRAM memory access energy becomes dominant. Why? Because your cache is tiny. So you need to access your DRAM again and again and again, right? So that is why DRAM energy excess energy is now pretty non-trivial. Especially this trend is actually more visible in the long sequence length. Sequence length of the 4096, meaning that a sentence or a certain paragraph includes 4096. The long sequence, now we need to access more and more DRAM so that the energy consumed from the DRAM is actually taking bigger portion. So now we aim to solve this problem based on in-memory computing. So if you do not know the in-memory computing, maybe let me explain in a single slide. So in-memory computing, the main idea is basically, unlike the conventional von Neumann architecture where the processor and also the memory are separated, now we are trying to sort of the merge. So the processing is actually simply done inside the memory without fetching the data. So this is the notion for the data intensive application, because in that case, the data movement takes so much energy and also delay. So in-memory computing is trying to compute in the memory. So generally, the memory, non-volatile memories are some resistance, based on resistance, we are storing the contents. And then the weight of the neural network model will be programmed in terms of the resistance as shown here. On the other hand, your input activation, inputs will be given as a voltage. Then just simple equation, V1 divided by multiply 1 over R. V multiply 1 over R. This is just high school, electric course, right? And then the current is actually V multiply 1 over R. 1 over R is G1, which is conductance. So this current will be V1 multiply G1 and V2 multiply G2. So those current will be summed up at the end. Then can you see here, this is exactly the form of the dot product. So in this manner, we are performing the dot product in highly parallel fashion. In this motivational example, there is only 2 rows. But in reality, can you see here, there are tons of rows per column. And also there are tons of columns as well. So both column-wise, row-wise, we have huge parallelism. So that is why we can achieve very high throughput. On top of that, each memory bit cell is actually very tiny. So in the memory world, the density is everything. So because of that, generally, the memory device is tiny and tiny. So we are computing based on that small the dense device. So because of that, the computing density is also very high. So if you later, take a look at the in-memory the papers, then you will be surprised at how small the chip is compared to the digital processors. So to summarize the benefit once again for in-memory computing, data movement reduction. We don't need to explicitly fetch out the contents outside. And also, all of the computations are using very low voltage swing analog voltage instead of the digital computation like either 1 or 0. Now this voltage is using very small analog voltage. So because of that, we can enjoy the very high computation energy reduction. And also, as I mentioned, row-wise, column-wise, parallelism, and high compute density. But the problem is, generally, this type of the low voltage swing-based computation suffers from the low precision and low accuracy. Why? Because analog computing is more sensitive to the many different type of noise. And also the ADC problem, because we need to convert the data from analog domain to digital domain frequently. So because of that, now ADC energy consumes actually pretty big portion. Well, this is another big problem. So previously in my PhD study, I fabricated a lot of the in-memory computing prototypes, reconfigurable in-memory computing, and also the inference processor for the traffic sign recognition. And also sometimes I embedded the trainer inside the chip. And also, so because of that, now the chip is actually learning for the time varying environmental parameters like a temperature, voltage, and many others. And also later, the recurrent neural network. So now we are trying to apply this principle to solve the data movement problem of the transformer. So we already learned that we do not need to send all of the contents exhaustively, but there is only key contents. So we don't need to move everything, but we only bring these key contents to the processor. So to do so, we need to have a certain rough computing capability in the memory. So through this in-memory computing, we are doing sort of the in-situ pruning, in-memory runtime pruning, which token is garbage. And then only the key pruned data will be delivered to the processor. And then only those are recomputed with high precision computation once again to maintain the accuracy. So this is the basic data flow. Then now your natural concern is it really okay in terms of the accuracy? Because I just mentioned that in-memory computing is generally has some accuracy issue. So this would impact on the accuracy or not. Fortunately, this operation has a lot of error resiliency. The reason is, based on this computation, our conclusion is whether this is garbage or important. So this is sort of binary decision. So this type of binary decision generally has very high error resiliency. We just merely make a decision whether this is pruned or not pruned. So because of that, as shown here, in terms of the output bit precision, even if we provide 4-bit equivalent resolution for the output of the dot product, still the accuracy is pretty well maintained as shown here. So we can say that the in-memory pruning operation has pretty high degree of error tolerance. So this is actually great opportunity to exploit the in-memory computing's the high parallelism and also low power, given this error resiliency. So detailed architecture is as shown here. The query vector, I gave an example like a module swipe, LE, and so on, and LE related query is actually broadcasted all of the columns, and each individual column includes the K vector, K1, K2, K3, and so on. So maybe modules, wife, LE, blah, blah, and so on. And then now QK1 dot product for first column, QK2 from the second column, and so on. We perform this kind of dot product column-wise parallel manner. And then at the end, we merely compute the binary decision. This is bigger than threshold or smaller than threshold. So we are making the pruning decision. Here, so I told you that ADC is actually a big problem in the in-memory computing. Given my experience, as soon as you attach the ADC, then your benefit of the in-memory computing, half of the benefit is gone because ADC is so expensive, analog to digital conversion. So, but instead here, we don't need to convert to the digital analog to digital conversion, but we merely compute simple comparator. So because of that, the energy consumption is nearly negligible. And another problem is, let's assume that K2 vector was unpruned. This is important token. Then this K2 need to be fetched and then need to be delivered to the digital processor, as shown this figure, right? There's some important contents we need to fetch from the memory and we need to deliver to the processor. But K2 was unpruned. But usually it is rule of thumb. In the memory device, we cannot fetch the column-wise direction, but memory device can fetch the data which is stored row-wise direction only. So because of that, we need to solve this problem. But fortunately, we use the ReRAM-based memory, and then ReRAM is actually symmetric. So because of the symmetric nature, we can implement transposable memory. So while we are doing in-memory computing, the vertical line becomes bit line. On the other hand, in the fetching mode, the horizontal line becomes bit line. On the other hand, vertical line becomes word line. So those are sort of the transpose, the role. And based on this nature, we can now successfully fetch out the contents stored in the column successfully. Okay, and we also found another good opportunity, which is the spatial locality. So this figure shows that, let's say for first query, the is given. And then we are dot producting with all of the other tokens as shown here. Then which token is unpruned? The unpruned tokens are marked with the blue color as shown here. Now let's move so in this case, because those are unpruned tokens, unpruned token contents should be delivered to the digital processor. Now we are moving to the Q2. Here, now again, the unpruned contents are these contents, meaning that more of him and also the appear in those tokens should be delivered to the main processor. But here, as you notice, there are very high overlap between two neighboring tokens, the and more. Can you see? These part are common, these common, and common, common. So we only need to, so in this case, actually, the overlap between two neighboring tokens, the unpruned position is higher than 80% as shown here. Which means that when we compute the Q2, already these contents are in the on-chip cache. So we don't need to bring again. Why? Because while we process Q1, those contents are already delivered to our cache memory. So those can be just reused without fetching again. Now this is the accuracy ablation study. So this is the baseline. And now this is the runtime pruning. And then here, if we only rely on analog in-memory computing, the accuracy drop is actually this much. But now, because we have the in-memory, the digital recomputation, this accuracy is rebounded up to here. So now, virtually, there is no accuracy degradation based on this type of the digital recomputation. So based on all of those techniques, in-memory computing, and also using the local, the the spatial locality, 95% of the data movement reduction could be achieved. And also based on that reductions now, 7 times speed up and also nearly 20 times energy reduction can be achieved at the same time based on this technique. So again, to summarize, we only we perform in-memory rough approximate pruning in the main memory. And then only important P token we fetch it to the digital processor and we compute again. So then we could reduce the 95% of the data movement. So this is the summary of this project. Okay, the very final, the research is the bridging sparsity and regularity in accelerator. So this project has been published in the CICC this year. So the project name is FreeFlex. So the sparsity is not new. Sparsity is known concept everywhere, right? So you might be very familiar like the structured sparsity and unstructured sparsity. Sparsity means that there are lots of zeros, right? And on the other hand, so if you think about the digital AI accelerator, nowadays the mainstream digital AI accelerator, which is most widely used in industry, is this type of the regular shape, regular processing element array. So we so-called 2D systolic array style. And then each processing element computes the MAC operation, multiplication, and addition operation as shown here. So this is actually very widely used, like Intel Nirvana, IBM Sentient, Google TPU, and Samsung, and almost actually all of the products are basically using this kind of mainstream. So this is actually pretty widely used because the input activation is actually delivered first column, second column, third column, and so on. So this input vector X is reused a lot. And also once weight is loaded into the local register of the processing element, those weights are also reused across many of the incoming vector of the X. So, and also as you can see, data flow is super simple, and control overhead is also low. And another beauty is each processing element is actually pipeline boundary. So vertically, horizontally, there are pipeline boundaries. So it is actually, once you synthesize this type of the systolic array, you will feel that frequency is actually very high. So it is actually perfect to improve the throughput. So but the problem is, as I commented briefly, now there is a notion of the sparsity. The position of 0 is actually quite random. And not only the input, but also weights. There are very high sparsities. Sparsity meaning that many contents in the vector is 0. And even more, the bigger problem is actually not only the unstructured position of the sparsity, but also the variation is pretty huge. As you can see, even within one network model, layer by layer, sparsity fluctuates a lot. And even different layers, not only the layer, but different models, the variation might be even bigger. So this type of regular structure is unfortunately not really good match with the unstructured sparsity problem, because those are actually operating with the same instruction and same operation. So it is actually very hard to skip a certain rows computation, a certain columns computation based on sparsity. So the goal of the project is actually we want to maintain this mainstream, the 2D systolic array style. But how can we use this opportunity to boost the performance? So this is our major the goal of this project. And another problem of the sparsity is, let us assume that okay, based on a certain technique, we successfully skipped the computing from the PE processing element. Whenever there is a 0, we can actually skip the computation with a certain technique. But even assuming that in this case, whenever the sparsity is very high, the large number of processing elements might be skipping, meaning that those are idling. Because of that, there is a huge unused power slack. Let's assume that there is a power budget. Generally, if you use any battery, there is a power budget, a certain milliwatt. Or if you connect with the PCI connector, then generally it is 75 watts. Then there is a power budget, but whenever the sparsity is high, many processing elements are idling. Because of that, lots of the power portion is unused. So this is actually, we are losing the opportunity to boost the performance. So our motivation is whenever the sparsity is actually very high, as shown here, we can boost the frequency to be twice. If the sparsity is low, then we can maintain the original frequency. Or if the sparsity is in the middle, then we can improve a little bit of the frequency. So basically the frequency we can adjust dynamically based on the input sparsity and also weight sparsity, so that we can fully utilize the power budget as shown here. Earlier, we had a lot of power slack, but now this unused power slack is used to boost the frequency. Now there is one more problem. So can you see from this figure? The sparsity of the input would fluctuate every single cycle. Then ideally, we need to change the frequency. Here, fast frequency, low frequency, middle frequency, and so on. Every single cycle, is it possible to change the frequency? It is impossible. It is actually not feasible. So we need to, if we modulate the frequency, we need to maintain that frequency long enough cycles. So what we did was in sparsity-based input reordering. So we reordered the inputs based on the sparsity to cluster the inputs with the similar sparsity as a group. So as you can see, we grouped the high sparsity inputs, middle sparsity, and also low sparsity as a group. By doing so, we can maintain the same frequency for a long enough cycles as shown in this motivational figure. Now your natural question might be, oh, then if we reorder the input, doesn't it impact on your functional accuracy? So actually our answer is it doesn't impact. This is conventional computer vision CNN data flow, weight stationary data flow, which is the most widely used method. So in that case, what we do is generally, let's say that the input feature maps coordinate 1, 2, 3, 4, and so on. And then for the first coordinate is given first cycle. So these contents will be given first cycle. And second coordinate will be given second cycle. Third coordinate will be given the next cycle. So this is the typical manner. But there is no need, no necessity to process in this order. So instead, what we do is we reorder based on the sparsity. So instead of the 1, 2, 3 order, 8, 7, 2, and so on, based on the sparsity. So in that way, we can send the similar level of the sparsity groups in the consecutive cycles. Earlier, it was actually fluctuate a lot, but now we can group them as shown in this figure, so that we can maintain the frequency for a long enough time. And this is the same in the natural language processing transformers. So when we process in general, we process token by token, Ellie's wife, Moriel's wife, Ellie, and so on. But there is no need to process in that order. We just reordered target sister, Ellie, and so on. So once we reorder the input vectors, and then when we save the data to the output memory, we simply need to store the contents in the right position, right address of the output memory in consideration of the reordered input, the address. So based on, in consideration of the reordering, if we store at the right address of the output memory, then it doesn't impact on final accuracy or result at all. So the architecture is as shown here. Once a certain layer is computed, we quickly check the sparsity. And then each individual output vector, we store the address. For example, a certain output vector's sparsity is very high, we send the address to the first FIFO group. If the sparsity for a certain vector is very low, then we send to the last FIFO group. So in this implementation, we had 5 FIFO groups as shown here. And then so here, we only store the address because contents is too large. So we cannot store inside FIFO, but only tiny address is actually stored based on the sparsity groups. And then later, when we process the next layer, there now we fetch out. For example, first FIFO contents will be computed all. Then once we finish, and then the first FIFO will be computed with very high frequency. And then now we move to the second FIFO. And second FIFO contents will be computed with a little bit lower frequency. And then the last FIFO will be computed at the last, and then that will be processed with very low frequency and so on. And also this is the specialized processing element. So many people are confused, and my students are actually confused. If the input is 0, then they think that the power saving is automatically achieved, but that is never ever true. So power consumption coming from the toggling of the node, not coming from 0, but toggling from the node, the power consumption happens. So even though there are lots of sparsity, let's say 0, non-zero, 0, non-zero, those are actually fluctuating a lot, then power consumption is actually even increasing. So for that reason, we designed the specialized processing element for the sparsity. And then whenever the input or weights are 0, then we can just we can bypass those multiplication and addition efficiently without toggling any of those internal nodes. So I saw many papers are trying to skip the multiplication, but because of the quantization, nowadays accumulation is more expensive. So it is very important to skip both multiplication and accumulation together whenever the contents are 0. And also based on all of those principles, so whenever the activation is 0, we can skip the computation. We could achieve 50% power savings. And when the weight is 0, we could achieve 60% of the power savings. And this is the measured result from the silicon and tape out in a 65 nanometer CMOS process. Now, based on our technique, can you see here, when the activation sparsity goes up here, now the power consumption monotonically decrease. So this is because of our proposed processing element. And also when the activation weight sparsity is getting lower and lower from top to bottom, power consumption is also decreasing. So now that we achieved the goal, now assume that this was actually measured at the fixed frequency. The frequency modulation hasn't been applied yet. Now let us assume that our power consumption is 800 milliwatt, for example. Power budget is 800. Then this amount of the contents are actually unused power slacks, right? So these are unused power slacks. So now what we're going to do is we will burn the entire 800 milliwatt by boosting the frequency. By using that unused power slack, we are boosting the frequency. So the frequency increase is up to 1.8 times as shown in this chart for based on sparsity. Of course, when the sparsity is very high, the frequency boost might be higher. Right? So given this technique, now the test is with real world the data sets. So for example, the VGG19, it seems that input sparsity is actually 75 to 85% is actually most common. And also the glue MRPC data set, 90 or 100% group is actually very common. And then we could achieve around near 1.6 or 1.5 times speed up. On the other hand, the overhead is as shown here, the power overhead. we added some special part like a FIFO and also the sparsity recorder and so on, those kind of things, additional part. But this takes only 7%. However, what I want to emphasize is actually because this is the silicon tape out from academia. So because of that, our scale is small, 32 row and 16 column systolic array. But in reality, in industry, people use like a 64 by 64, a little bit bigger processing elements. So in that case, I'm sure that this overhead will be way more amortized. So in that case, I'm sure that this percentage might be like a 1 or 2%. And also, the measured result is we could achieve up to 1.1 gigahertz at the supply voltage of the 1.2. And then we supported the 8-bit weight and input, and also 24-bit partial sums. And then we could achieve around up to 1.0 TOPS per watt, and the minimum 0.6 TOPS per watt. Those varies based on the sparsity of the input and also weight as well. Okay, so this is the summary of the very final project. So we wanted to achieve some performance benefit at the wide range of the sparsity, not only the high sparsity, but also very low sparsity level. We should not lose the benefit. We should not lose the energy efficiency. Indeed, we achieved, can you see here? So only 2 or 3% of the energy overhead, even when the input and weight are non-zeros. So we didn't lose any the energy efficiency, even for the non-sparse data. And also, we really wanted to maintain the regular mainstream accelerator structure. So based on that, we explored the frequency boosting by utilizing unused power slack. So we could achieve 1.8 times performance boosting with 7% power overhead with the 65 nanometer CMOS process. Okay, so that is all from today, and thank you so much for listening to my presentation. And these are some semiconductor chips that I have been working on. And then please visit our website, ucsandiego.vvip.com. So anyone, do you have any question or comment or feedback? Yeah, it would be greatly appreciated. Yeah.
Thank you, Mingu. Thank you very much for this wonderful talk. Yeah, so any questions from our audience? So you can unmute yourself or input your question in the chat box.
Hi,
Professor,
this is Mingu. I'm sorry, go lady, go first.
Oh, thanks. I have Professor. I have one question for your first work. Actually, it's because the internet connection is kind of unstable during the talk. I guess I missed so much information. So I would like you to share more about the challenges for your first work. I'm not sure if it's the point is about the chaining of the threshold that you mentioned in the first work, and I'm confused that whether it's kind of hard. So like previous work didn't pay attention to that. So like I really didn't get the point of your first work. Like what is the highlight of it? I think it might have something to do with the threshold, because you mentioned so much things about the chaining of the threshold.
Yeah, right. So basically, we need to train the threshold. So based on that, we need to have some golden threshold to judge whether the token is redundant or not, right? And then the problem is, so now we wanted to include the threshold as a part of the network model. So the threshold is actually automatically trained, rather than empirically finding the threshold, all of the 96 layers one by one. We want them to be optimally found, and also boost the frequency, boost the sparsity at the same time. But problem is the threshold layer shape is like that, so it is not differentiable. Yeah, go ahead. Yeah.
Yeah, but I'm curious about like for previous research work publication, like others haven't paid attention to that. They always give a fixed threshold and never thinking about chaining it.
Yeah, so very good question. So before my publication, there were about a couple of projects which actually used a certain threshold. So before that, everybody empirically just swept for all of those layers with empirically swept. So that has actually two problems. Number one is, how do we guarantee the accuracy? Of course, that is number one. Another one is, all of the other parameters have been already fixed, and then only changing the threshold. So it doesn't achieve very impressive pruning ratio. However, in our case, we train to boost the sparsity level as a part of the loss function. So in our case, parameter and train, the threshold are co-optimized so that our pruning ratio is actually much higher than the others.
So do you think if we get like empirical or fixed threshold, it kind of give you a higher accuracy or not? I still got a little bit confused about that.
Yeah,
I don't know, like whether other people, I think they may get some good reason so that they didn't pay attention so much to the threshold training, isn't it?
Oh, actually, yeah, this method was actually very widely used. The thresholding and then dropping. It is actually, I cannot count each individual papers. So because there are those are so popular direction in this domain, and then everybody was actually empirically finding those thresholds. So that is why I studied actually this research. And then you commented the accuracy. So our goal is, we are not trying to improve the accuracy, but we are maintaining the original accuracy for the before pruning result. So before pruning result is actually here, and our accuracy is actually well maintained even after we prune out the 75%. Right?
Yeah, thanks. And also, I have a question about the sparsity. I think that's a quite cool work. My understanding for your third work is that you want to improve the power efficiency. So we try to introduce the frequency modulation to like get rid of the sparsity. But do you think we can think in the other way? Like so when the sparsity is very high, can we think in that situation the static power consumption is low, so it's actually a good thing or not?
I see.
I'm pretty sure in your case it's a terrible thing, so you actually try to use adjust the frequency. But can I think the other way around? Like I think it as a good thing because in that situation the static power is low.
I see. So yeah, good point. So you are saying that here sometimes the sparsity is high, so we just let the power consumption to be low, right? So then
so I know there is a power slack, but like if I don't use it, I let everything be off, then the static thing is low, and I think that's good.
So this is actually two different scenarios. Number one, server platform. Server platform, anyway, the AI chip is actually supposed to be plugged in your motherboard, right? And then that is connected through the PCI connector. Then PCI connector anyways provides 75 watt. If we do not use, then it is actually not so good. Why? We need to anyway fully utilize the power to boost the speed. Because anyway, 75 watt is actually continuously given to us, right? Maybe if it is the battery operated scenario, if we use actually this case, then battery lifetime will be increased. On the other hand, our goal is Now let us try to boost the speed. So in the regular array architecture, actually skipping is somehow possible. This is actually sort of possible, but it is known to be very difficult to boost the speed. So our goal is for those kind of both server scenario and battery scenario. Now we are trying to maximize the speed by fully utilizing the budget always. Right?
Okay, I see your point. Thanks, Professor.
Yeah.
I think we have some other questions in the chat box and also some questions from. I think that someone just want to speak out. Yeah.
Hi. It's very nice work, Professor. Could you explain more about the reordering of the data according to the sparsity? Would that also cause like pre-processing of the data? It also costs power. Could you explain more about that?
I see. Yeah, actually, good point. So reordering is actually done in real time, on the fly. So it doesn't require any pre-processing. But when we finish the previous layer computation, just output comes out, and then real time we check the sparsity, and then based on that we just move the address. We classify the address based on the level of the sparsity group on the fly, real time. So as I commented, now indeed, yeah, this consumes power. So yeah, like 70% here. But I think that this is a little bit misleading number because our processing element core is too small. If it is actually bigger as normal, then I think that it should be even smaller because that part is actually merely nothing special, but only five cores. So in that sense, the overhead is actually super low. Delay-wise, there is a zero delay because everything is actually on the fly. Those are actually computed in real time. So delay-wise, indeed, actually zero overhead. Yeah. Does that answer your question?
Yes, thank you.
Okay. Yeah. Thank you.
I think some other questions in the chat box. Can you see that?
Okay. So some.
Yeah,
some students asked whether do you apply specific threshold or threshold varies. Okay, during the training threshold varies, of course, because we are training, right, the threshold. So threshold indeed actually varies over time. Each individual epoch as shown this figure. On the other hand, once we finish and then accuracy is good and sparsity is very high, like from the training data, like 80%, then now we finish. And then those fixed threshold for each individual layer and also head now is just fixed. And then those fixed contents will be used for the inference in the hardware. Yeah, hope that this answers the question. And then, yeah, and also the Yu Gong asked whether threshold is learned offline or learned on the fly. So yeah, that is actually, as I just commented, it is learned from the offline, from the training process, like a GPU or somewhere else. And then for the inference, now the threshold does not need to, be updated any further because those are already completed, right? So those are now actually good enough. Okay. And then also asked, I'm curious whether the threshold needs a training process. Yes, right. The training process is required. The threshold indeed needs a training process. So that is why this training is actually optimized to for what goal? The goal is to maximize the sparsity more and more. So training is actually the threshold is learned and sparsity goes up. Then how we achieve based on this kind of loss functions modification. Yeah. Okay. So yeah, a certain student asked that, do you have any vision on the future AI chip design, either hardware or software related? Yeah. So I think that, to be honest, long term, it's very hard to say. But anyway, because the network model is changing over time, it's very hard to predict. So nowadays, even industry and also researchers, their goal is to make it as flexible as possible. So that is the only the viable direction right now. If we think about earlier fully connected layer, which is actually highly data intensive, not compute bounded problem, but memory bounded problem. And then later, convolutional neural network came out. That is not really memory bounded. Memory consumption is like a 5%. It's pretty small. So we thought that we solved this problem. And then later, now the BERT and transformers actually came out. And those are again the fully connected layer. However, even there, we can reuse the data. So it was actually okay. But later, generative model came out. So in the generative model, again, it is actually a memory bounded problem, right? So indeed, it's very hard to expect, but I think that generally speaking, flexibility is very important. And then flexibility important not only to cover wide variety of the machine learning models, but also in terms of the processing element utilization. Let's say that the array size is 64 by 64, but your input feature map was like a metric size is a little bit different, then many of those processing elements might be unused, unfortunately. So those kind of flexibility is actually also very important for the processing element utilization perspective as well. Yeah. Hope that my answer is actually satisfying. Yeah, viable. Okay. Yeah. Any other question?
Some other questions from the audience? If no more other questions, actually, I have some questions for you.
Sure.
Yeah, so in your talk, so your first part, you mentioned you introduced that the sparsity aware transformer design, and the second part is about the like in-memory computing design. So I was wondering, we know that so right now the GPT already evolved to the from GPT-2 to the GPT-4, the model size increased, I think maybe more than 1,000 times and so on. So and we know that according to scaling laws, the model size for those LLM model will continue to scale up. And I was wondering, so in this, regarding about this trend, so as the hardware designers, so how should we incorporate this rapidly increasing model size and computational complexity at the edge? So like we know that, so right now the model, we cannot store that in the SRAM at the edge, right? And we know that the data movement is very expensive here. And you mentioned about the in-memory computing. And we know that, so even use like in SRAM computing or in RM, still the memory size is not like large enough. So do you think, considering this trend, whether what we can consider about like the in-DRAM computing here, like we store all the parameters in the large chip DRAM, and then to explore the possible optimizations that target for those for the accelerators of the GPT-4 and so on.
Yeah, right. So give me 1 second. So you commented that the problem of the scale, right? Scalability, right?
Yeah.
So indeed, I think that so when I was in IBM, actually one of the very important topic was actually achieving the problem. So we try to make a scalable version as much as possible. And then let's say that if we have 2 cores, then the performance becomes twice. And if we have 3 cores, then performance becomes 3 times. So it is not like that, because there is actually a lot of overhead, and then the performance improvement is actually not linearly increasing, but it is actually quite saturated, right? So actually, we should actually maintain that kind of the scalability as much as possible, right? And then, because of that, we applied tons of different techniques like compression, and then also the core-to-core communication a lot, actually. So one important topic of my work in the IBM was actually the core-to-core communication and data compression, and they interconnect each other, right? I think that, but there is no actually magical solution in my view. Anyway, it should be done like an algorithm, and then in our team earlier there was the on-the-fly compression technique to deliver only the key contents of the gradient as well. So I think that I'm sure that if the model becomes bigger and bigger, I'm sure that there are more and more
sparsities. Like, the 4,096 words, then how many of those are related? So recent to the research by Professor Song Han, many others, when I take a look at, rather than taking a look at the entire word, they check very recent word and the very beginning word, because the key important, the contents is usually at the beginning of the paragraph, right? And then those and then recent contents, they combine and then only check those two contents and then make a decision. I'm sure that the type of the algorithmic technique related to compression, the model compression and simplification, and also the data extraction, those kind of technique might be actually key in the future.
Okay. Thank you very much.
Thank you.
Any other questions from the audience? Okay, so if no more other questions, let's thank Professor Kang again for this very wonderful talk, and also thank everyone to attend our this week Efficient AI seminar talk. So see you next week. Okay.
Okay. Thank you.
Mingu.
Thank you.
Bye.
Bye.